So let's look at learning objective B, and we're going to state the multiplicity of various zeros of a polynomial. So on this slide, what they're doing is they're taking the equation of this graph right here, and they're just changing it and looking at when n is different values. So they're going to go in here and change this exponent to 1, 2, 3, 4, or 5. So let me just show you on this first one. If n is 1, what the equation actually would look like is y equals x plus 1, then x minus 2. And we can tell that the two factors are here and here. If we found their zeros, by the way, the 0 here would happen at -1 and at +2. So it's a little hard to see, but there's one here at -1 and there's one here at +2. So it's a second degree polynomial with two real zeros. Now the second one here, if n is 2, here's what the equation would look like down here. It would be x plus 1 and x minus 2 squared. Now if we wrote this out longhand, by the way, it would just be x plus 1, it'd be x minus 2 times. So this is actually a third degree polynomial, because if I multiply it through, the highest exponent will be 3. So that means there's actually going to be 3 real zeros here. What are the 3? Well, if you take the factors, this factor will make the 0 be -1. This factor will make the 0 be 2, and this one will be 2. So what happens here is there are 3 zeros. One of them is -1. The other is the number 2. What we're going to say is with multiplicity of 2, because the number 2 happens twice. Now I'm going to jump right over into when n is 4 over here. So when n is 4, here's what this one looks like. X plus 1 and x minus 2 to the 4th power. By the way, if we multiply this out, will become one big term. There's 4 and there's 1. This is a 5th degree polynomial. There is going to be 5 real zeros for this one. Well, like the other, if I were to write this out longhand, it gets a little long. You're going to see x minus 2 actually happen 4 times, it says here. So if someone asked me to find the zeros, I would take this factor, set it equal to 0, and I'd get -1. So one of them is -1. But then notice here, this guy's going to be 2, 2, 2, 2. So here we have, the other 0 is 2, but we would say it's with multiplicity of 4 times. So what we've done is we have accounted for all 5 of the zeros. One of them just has a multiplicity. So the 4 multiplicity there in this individual one gives us the 5. So let's actually look at one that isn't in a nice factored format. First thing I do want to highlight here are these theorems right here talking about the fundamental theorem of algebra and the number of zeros. All you want to glean from this is really this statement right here. It just says a polynomial of degree of n greater than or equal to 1. So anything that is at least linear or higher has exactly that number of complex zeros. Remember, a complex number can be real or imaginary. It's a combination of that. So if you have a 5th degree polynomial, there are 5 zeros. If you have a 1st degree, there's 1 zero. If you have a 2nd degree, there's 2 zeros. It could be a mix of imaginaries and reals or just complex numbers. That's all this says. So when I look at this equation right here, and they want me to find the zeros, I know exactly how many answers there should be. There are 3 zeros. Now what I don't know is if they're made up of real numbers or imaginary numbers. Now the real numbers we can see when it crosses the x-axis. So what I'm going to do is graph this. When I graph it and put it into a calculator, here's what I see. Now it looks like there's a very obvious 0 right here, and it looks like there might be another one right there. Keeping in mind there's 3 of them. So I can see 2 of them on the graph paper here. Here's one of them right here. If I go to the table, by the way, one of them is at 0. Here's another one on the table. Remember, the y has to be 0 at 12. So one of the zeros is 0. Another one is the number 12. So the question is, where's the third one? Well, one of the ways to probably look at this is to see if maybe you can actually factor this into the algebra. So if you take a look at this third degree polynomial, we can actually pull an x out of everything. So let me show you where we're going to get the three answers. Pull out the x, so I'm left with x squared minus 24x plus 144. Now to find the zeros, I just set that expression equal to 0. This trinomial here can be factored further. There is factors of 144 that will actually add to negative 24, and here's what it looks like. If you break it up, this x squared has to go here and here. Factors of 144 go here and here. And those factors are going to be a negative 12 times negative 12 is positive 144. Notice this, when you check those two, they add to negative 24. So all you do now is you take the three individual factors and set them equal to 0. So x equals 0, x minus 12 equals 0, and another x minus 12 equals 0. What we're going to get for our answers is 0. This will become positive 12, and this will become positive 12. So here's the key. The graph actually showed all three zeros. We just couldn't see the multiplicity in the graph, and you never can see the multiplicity. This thing technically is kind of crossing at 12 twice, but I can't tell. I had to actually do the algebra to prove it to me. So if they ask me what the zeros are, what I would say for this, there's one at 0, and then it's 12, I would say with the multiplicity of 2 would be my final answer for this problem. Let's look at one more of these. Here we have a polynomial. This is a 15th degree polynomial, which means there are exactly 15 zeros. So what I'm first going to do is maybe graph it. When you graph this, here's what you get. And it looks like to me I can see one of them. It's probably there at the origin. So if you look at the table, I can confirm that y does 0 out at 0. So one of the zeros is 0. Now, maybe that thing happens 15 times, but maybe it only happens once. I don't know. What I'm going to do next is actually look at this equation to see if I can do some nice algebra. And you can actually pull out a greatest common factor of all three of these. At the most, I can yank out 13 t's. So I'm going to go ahead and do that. T to the 13th, we're going to pull out, and so we're going to have 9x squared minus 6t. Be careful, when you take this out, there is a number there. It's the number 1, so it's plus 1. And they want us to find the zeros, so take the expression and set it equal to 0. Okay, I'm going to keep t to the 13th here. This is factorable, by the way, into two groups. I have to take 9t squared, so t and t go here. I need factors of 9. It's either 9 and 1 or 3 and 3. I suspect it's going to be 3 and 3. And then I have to take two numbers that multiply to a positive 1. They're going to go here and here. So it's either 1 times 1 or negative 1 times negative 1. But I have to do it such that when I multiply these two, I get the middle term of negative 6t. What that's going to be is negative 1 and negative 1, because look what happens here. Those add to negative 6t. So I have it. Now, what I need to do are just take the three factors that I have here and set them equal to 0. So t to the 13th is this. I'm just going to write this one once because I see it happens twice. If I solve this one, I'm going to subtract 1 or add 1 and then divide by 3. So this is 1/3, and I'm just going to write this now with a multiplicity of 2. So I have 2 of them. Now be careful. How do you get rid of the little exponent of 13 here? Well, you multiply by 1/13 as a little exponent. That's the 13th root. You can actually type this into your calculator though. What you would type is just 0 to the caret, and then in the parentheses 1/13, it's going to be 0. So the answer to this one is t equals 0, but with the multiplicity of this one happens 13 times. So therefore, I have just accounted for all 15 zeros. 0 happened 13 times, 1/3 happened 2 times. By the way, the 1/3 on this on the graph was very hard for me to see, so I couldn't rely on that to get all of them.